what happens is that water starts to move back and forth. It builds up pressure within the body itself of the water. As that pressure builds up, what it can actually do is take those soils, those individual particles, and they'll actually lift them up. So instead of having this soil that's kind of, one soil particle resting on top of the other, the water will actually force particles to actually float. And for that instantaneous amount of time when those particles float, then all of a sudden the whole stratum responds more like water than it does a solid, because the particles are no longer really touching each other. And that's what happens in liquefaction. Okay, so yeah, it takes on the properties of water, so to speak. Okay, so and these areas shown here are in green are the areas that are prone to liquefaction. In other words, these are soils that have been mapped that maybe there's a potential that these soils could liquefy during a major earthquake. And so these are some things that we're going to evaluate. Now, of course, there are ways around that to fix that. If we know we have liquefiable soils, there's a lot of ways we need to build the foundations or improve the ground to prevent the soils from actually turning into liquid during an earthquake. Over here in the light blue, it might be a little bit hard to see. These areas are mapped in the light blue as potential landslide areas. Again, with landslides can be triggered by a number of different things. Strong vibrations and the earth actually shaking, if you have a loose soil mass, can end up actually causing or inducing landslides. So again, these are areas that are of concern that really need to be looked at if you are going to be doing new construction and new building. And if you happen to have a house that's existing, if they didn't take that into consideration during the original design, that it is something to consider. That this house, under seismic or a big earthquake, there may be some issues with the stability of that house. Landslide maps. You guys, this is again in the Palos Verdes area. So some of you guys may recognize the Portuguese landslide here. The red ones are the active slides, ones that have moved in more recent history. So again, if there's been shown movements, again, there's a number of slides. These kind of yellow ones are ancient slides, ones that haven't really shown any movement, but the geomorphology, the geology of it, we think that this landmass has moved sometime in geologic time. Again, geologic time, thousands to 10,000s to millions of years. Some time ago, this land had moved, and it's pretty stable now. But again, whether or not it should move again in the near future, it's kind of unknown. There's a potential. Obviously, the active ones, there's a much higher risk of those moving in the future. So those are some of the background things we typically look at. Now I want to talk a little bit about soils. I call this kind of like the soils 101. Soils is not dirt, okay? Technically, it is a bunch of little particles. And soils actually are made up of three components. There is the actual particle themselves, the soil particles, the solids. There's a liquid phase of it, which is typically water that's in the ground. Like if you pick up soil, it's kind of moist. That's the water. You're filling that water. And there's also a void space, which is the air, okay? Most soils, or typically all soils, have all three of these aspects. Unless the soil's like underneath the ocean where it's completely saturated, where all of the voids are filled with water, then we have a two-phase item. We have just the water and the soil particles. But how it's important, because all three of these properties and how these three items mix together depends or determines how these soils are going to react. What are some of their engineering properties? What are their strengths? How stable are they going to be if they're on the side of a hill? Those types of things. So real briefly, where does the soil particles come from? Well, ultimately they originally started as part of the earth crust, as rock. As the rock disintegrates or weathers, they become smaller little particles, and these particles then end up making, again over geologic time, the soil that we see today. The soils that the plants grow in, that we walk on, even the sands of the beach. Okay, so the type of the parent rock, where these soils were derived from, are really going to tell us a lot about the engineering properties of these types of soils. And from an engineering perspective, we really divide soils into two categories. Now, there's different types of classification of soils for agriculture, things like that. But from an engineering standpoint, for building construction, there's essentially two types. Soils will fall into one of two areas. One, either cohesive soils or cohesionless soils. I have backwards. Cohesionless soils or cohesive soils. And essentially the difference is the cohesionless soils, these are sands and gravels. Okay, these are, the beach sand. If you go down the beach, pick up the soil, you can actually see the sand particles. Those are cohesionless soils. Cohesive soils, again, they're also very they're all comprised of individual particles, but they're so small that the normal person can't see them with their naked eye. So if you were to pick up some dirt and you could like put it in your hand, you can actually see individual particles, you're probably looking at a cohesionless soil. If you cannot see the individual particles, it's just like a big ball or a big mass, then that's probably you're looking more at a cohesive or a fine-grained soil. And the difference is how these materials behave. Real quickly, granular soils, again, the individual particles, when they actually touch each other, that's how these particles and these materials get their strength. They can be what's called well-graded. That's where you have a bunch of different size particles, small, big, large. Poorly graded ones are ones where most of the particles are about the same size. Again, beach sand's a great example of that. If you look at it, most of the sand at the beach is about the same size. There's not a lot of big boulders, big gravel pieces, and there's very little cohesion in the soils because all that stuff gets washed away by the wave action. The density, how close knit or how close together these particles are in the area that they're at, will determine how strong the material is. Again, a very loose soil is not as strong as a very dense soil. Fine-grained soils, again, these are oftentimes intermixed, and these soils will, again, they're oftentimes mixed with granular soils, and how they are mixed up and what the percentage of will determine how these materials react. This is just a soil classification chart that we use for engineering properties, but officially, if you guys are ever interested in knowing when we talk about boulders and cobbles and gravels, there is actually a technical size on what those materials are. If it's less than 3 inches or greater than 1/4 of an inch, that's officially a piece of gravel that you're looking at. So not too much there, not too much interesting things there, but soil expansion and settlement. This is really now, we're going to talk a little bit about how the actual soils and the properties react, okay? There's two types, or a number of types of settlement mechanisms. Essentially, settlement is just really movement downward due to gravity or other forces of the soil. Elastic settlement, this happens in sands. Again, since we're close to the beach, I have a lot of beach analyses. Elastic settlement is probably best described. How many of you guys had a chance to walk on the beach sometime in your lifetime? Excellent. Have you guys ever turned around and looked at the footprints behind you? As you walk on the beach, at least close to the water, you'll notice if you take a step, the sand immediately reacts. What happens, the sand's right underneath your foot, you're applying a load, pressure will actually settle. And you'll see your footprint. So all those sands have essentially done elastic settlement. They've immediately responded to the load that you applied upon them. So if you were to build something near the sands, most of the time, as soon as you put that load on, the sands are going to react right away. Consolidation, however, that happens in the fine-grained soils. And what happens with consolidation is you apply this load, but the soils don't react immediately. Why? Because there's water. Oftentimes there's water in the way, so they can't actually settle because the water is still holding them up, so they can't push their way down. So what happens in consolidation in clay soils actually takes a very long time. So if you apply a new load to clay soils, it could take months to sometimes years for the settlement to occur and to stop. And that can be very detrimental to building structures, things like that. Again, if we're having settlement, or more important, the differential settlement, that's when you start to see a lot of cracks in the buildings, you start to see a lot of distress with that. Other types of settlement, particle migration and dynamic settlement. Liquefaction is a type of dynamic settlement. Again, when there's a big seismic load and the soils respond or settle. I'd like to talk a little bit about consolidation. I mentioned that consolidation could take months or years. Well, what happens with soils, clay soils? Clay soils can be seen maybe it's like a sponge. Kitchen sponge, if you guys have a kitchen sponge in your sink. If you were like my roommate and I in college, we had this kitchen sponge that sat there for days or weeks, and as the piles gathered up. And one phenomenal fun thing happened. That sponge was always really dry and light. If you guys notice that if you have a sponge, you don't use it too much, it kind of dries out and becomes very light. Now if we were to take that if you can picture with me, this old kitchen sponge, hasn't been used much, very dry, we stick it on the counter. Then we take some water, just a cup of water, and pour it very slowly on top of that sponge. What's going to happen? Is the water's going to pour, it's going to expand. That sponge actually absorbs the water. So the water that we pour on top of it goes inside the matrix of that sponge. And a few things you'll notice. The sponge will physically expand.